Hello everyone, I am Shahib Kumar Dhar. Now I am going to discuss a very important thing in pure mathematics, that is comp space and deleted comp space. Actually, deleted comp space is more interesting than comp space itself. So what is comp space? Comp space looks like this. Okay, it looks like basically a comp of which many jaws are broken, and each jaw is of length 1 unit. Okay, so it's from 0 to 1. Basically the y-axis from y-axis 0 to 1 has been cut. Okay, and it's also from 10 to 1. It is basically the x-axis. From x-axis from 0 to 10 has been cut. Okay, it is half comma 0 to half comma 1. It is 1 by 3 comma 0 to 1 by 3 comma 1. So it's going towards, as much as n tends to infinity, it's going towards 0, and as much as it going towards 0, it is more dense. Okay, so it looks like this, and it is its explicit form of this space. Okay, you can watch it and note it down. Now I am going to the deleted comp space. What is deleted comp space? Deleted comp space is generated by deleting this set from the comp space. Okay, basically I am deleting all elements of this portion. It is 0 to 1 from the portion of y-axis except 0 and 1. I am telling another time, I am deleting all elements, all the points of y-axis present here except 0 and 1. Okay, then we will get the deleted comp space. Okay, actually this deleted comp space is connected but not path connected. I will prove it. First of all, to prove that deleted comp space is connected, I have to know another thing. Okay, this is a set, basically a space E. It is generated by deleting 1 point from the deleted comp space. Here is a deleted comp space, and I have deleted this point. Then I will get the space E, this space. Okay. Now you say me one thing. Basically, if you make closure of this space, then you will get the comp space. Fine, because if you take closure, then the y-axis will be included in that closure. Okay, so its closure is basically comp space, and it is a subset of, or basically subspace of, deleted comp space. Fine. Now this space E is basically path connected, because if you take any two points, it can be joined by a path, because every point of this E is joined by a path. Okay, so it is path connected, and path connected means it is connected. Okay, now to prove D is connected, look at this beautiful thing. This is a set E, and E is a subset of D. Okay, it's clear. E is a subset of D, that is deleted comp space, and deleted comp space is also subspace or subset of comp space. Okay, and what is comp space? Comp space is basically, C is basically closure of E. Now you should know a beautiful thing in connectedness, that is, if you take a connected set and its closure, then any subset between that connected set and the closure of the connected set is always connected. I am telling another time, any set that's between a connected set and closure of that connected set is always connected. It's look like if you take E, which is connected, and E bar, that is C, and if D is between these two sets, so D must be connected. Okay, that's why D is also connected. This is the reason D is connected, because it is connected, and so this set and its closure E bar, and D is between these two sets, so D is also connected. Okay. Now basically there are few more things, that is this comp space is path connected basically, because if you take any 2 points from this space, that can be joined by a path. Okay, this is basically path connected, and path connected means it is connected. It is also contractible. What is contractible? Contractible means the identity map and the constant map both are homotopic. Okay, so any path connected space is basically contractible. Okay, so it is contractible also, but it is not locally connected, it is not locally path connected, it is not locally contractible, because if you take any points from here and if you make a neighborhood, if you zoom it, it will be looks like this. Okay, it will look like this type. Okay, then look at this. It can't be joined with any path. If you take a point from here and a point from there, then it can't be joined by a path. Okay. Also, it is not connected. Also, you can divide it from here. This is an open set, and this is an open set. Okay, and these two open sets have disconnected this set. Okay, so this neighborhood also not connected, and it is not also contractible. Okay, locally contractible. That's why it is connected, path connected and contractible, but not locally. Okay. Now I am just going to prove that deleted comp space is not path connected. It is a very important example in topology. It is an example of a space which is connected but not path connected, and I have to prove it. Okay. So basically, I will show that my target. I will show that there does not exist any path joining 0 and P. I am labeling 0 1 as P. Okay, and I will show that there doesn't exist any path joining this point and this point. Okay, I have to prove it. 0 0 and 0 1. To prove it, I am assuming that if there exists a path, and finally I will reach to the contradiction. Okay, so I am taking, if possible, there exists a path F that is from 0 1 to the deleted comp space joining 0 0 and P. It is 0 1. Okay, if there exists a path. Okay, then I will show that my target or M. Okay, that is to show that F inverse P, this set F inverse P is both open and closed in 0 1. I will show that I want to show that F inverse P is both open and closed in 0 1, because if I can prove that, then it will contradict, because in 0 1 it is in real line topology the only sets which are both open and closed are phi and the whole space, but F inverse P is not phi or not the whole 0 1 at all. Okay, you can check it. It's a beautiful thing. You can check it. Okay, I am questioning mark why it can't be both open and closed in 0 1. Okay, now I am going to first of all, the thing that is clearly F inverse P is closed in 0 1. What is the reason? The reason is this P. This is a closed set in deleted comp space. Okay, it is a singleton set, and so it is closed because it is an Hausdorff space. Okay, and F is a path. Okay, so F is continuous. By the definition of continuity, if F is continuous, then its inverse image from a closed set should be closed. Okay, so its inverse image should be closed because F is continuous. So that's why F inverse P is closed. So my only target is now to show that F inverse P is open. Okay, to prove that I'm taking let X belongs to F inverse P. Okay, I'm taking that let X belongs to F inverse P. So that's why Fx equals to P. Clear? Now let V be an open neighborhood of P in D. Okay, let V be an open neighborhood of P in D. It's a very important thing that doesn't intersect x-axis. I am taking the neighborhood such that the neighborhood at the point P, this is my point, basically this point is my basically P. I am taking a neighborhood around it such that that neighborhood doesn't intersect this y-axis. Fine. Okay. Then fine. That's why this fx V is a neighborhood of P. Okay. So this P belongs to should be. Okay. I am writing it here. So this P should belongs to V because V is a neighborhood. So if fx belongs to V, basically this fx belongs to V, what it implies? It implies x belongs to F inverse of V, correct? Now you tell me that V is an open neighborhood So V is open in this deleted comp space, and F is continuous, mind it. So from this, F inverse V is open in 0 1, because V is open and F is continuous, so its inverse should be open. Okay, clear? Clear? So now, since it is open in there, so from and X belongs to this F inverse V, so between X and this set, there will be an element or a set from open base. You will get an element from the basis that is an open base. Okay, so there exists an open base U such that I am writing it here basically. X belongs to U, that is subset of F inverse V. Correct? Clear? So you get it like this. Fine. This basically implies, if you take this one, then it basically implies that F of U, okay, that is a subset of F inverse of V, and F of F inverse V is basically subset of V. Clear? It is not equal. Why it is not equal? Please check it. Okay, there is a small thing in everywhere, and you should check it. Okay, that's not always equal. That is a subset of V. Okay, so that's why Fu is a subset of V. Okay, now look at that one thing, that X belongs to U. Okay, so that means F of X belongs to F of U. Here X belongs to U, that's why F of X belongs to F of U. And what is F of X? That is P. So P belongs to F of U. Clear? Now my assertion, this is my assertion, I am writing it my assertion. My assertion is that F of U will always only be contained with P. F of U is only P. There is no other element other than P in Fu. Okay, so I will prove that. Okay, I shall prove that. How can I prove it? Okay, very clear. I am taking, let, if possible, there exists S that is not equal to P, that is other than P, and that belongs to F of U. Okay, I am taking, okay, there is any other element S that belongs to F of U. And what is F of U? F of U basically a subset of V. What is V? V is basically here. V is basically looks like it is a neighborhood. Okay, and F of U is basically, I label it as V. This is a neighborhood of P. I have taken already V be an open neighborhood of P. So I have taken V as an open neighborhood of P, and F of U is a subset of V. So F of U is basically subset of this neighborhood. Clear? So and S that belongs to F of U. Okay. So how this S will look like? So this S here, so S belongs to any of here. Okay, so this type of S is an element of basically deleted neighborhood, and S is not present in the x-axis because I have taken V such that V doesn't intersect with x-axis. So this S will always look like something 1 by n comma, it looks like 1 by n comma z. Okay, for some n belongs to natural number. Okay, and z belongs to, z is basically from this to this. Okay, so it looks like this. Now my work is to find an R such that R and a R between 1 by n plus 1 and 1 by n. Okay, so if I zoom it, okay, I am zooming it here. Okay, so what does it looks like? It looks like this. Okay, it looks like this. This type of, it looks like this. Okay, if I zoom it here, okay, and from somewhere S is present, I am assuming that this is my S. Okay, this is my S, and from in somewhere here I am labeling it like this. And somewhere here, this is my P. Okay, this is my P, and this is my S other than P. Fine. Then its abscissa is 1 by n. Its abscissa portion. Not I am not taking the ordinate. Its abscissa component is 1 by n. I have taken it like this, and this just left line is 1 by n plus 1. Okay, its abscissa is 1 by n plus 1, and I have taken R just between these two. Okay, so R is present somewhere here. Okay, this is my R. Okay, now if I break this neighborhood just like this. Okay, I break from R. From R, I am breaking it just like this. These two neighborhoods. Okay, I can explicitly write it down like this. I am A equals to minus infinity to R, minus infinity to R into capital R, and my B, I am taking B as R to infinity cross R. I am taking them to A and B like this. Okay, then these two sets separates this whole neighborhood. These two sets separates this whole neighborhood. Correct? It implies, which does it imply? This implies that this is my U is present here. Okay, my FU, sorry, my FU is present here. Okay, so my FU is something like this. I have zoomed it out, zoomed it in basically. So that's why from this I can write that FU is disconnected. Correct? Because it can be separated by two. It's basically open sets. It can be separated by two disjoint open sets. Okay, these two are disjoint open sets. That's why I can conclude that FU is disconnected. But there is a thing, that is, what is U? U is an open base. U is an open base in where? In 0, 1, in this space. And in this space, open base are the open intervals, and open intervals are always connected in 0, 1 or real line. Okay, so and my F is continuous. So F of U should be connected, because continuous image of a connected set is always connected. So F of U must be connected, but I am watching that FU becomes disconnected. So this is a contradiction. Why contradiction arises? Because I have taken that there exists another element other than P in F of U. So from here I can conclude that there doesn't exist any other element other than P in FU. Okay, so I am just using the lower things because I have already go through the thing. Okay, I am using this one. So from this I can say that basically F of U equals to only P. From here I can tell that what kind I can say that is from that one I can say that F inverse of F of U, that is equals to F inverse of P. Correct? Because both are same, so its inverse will be same. So okay, and F inverse of FU, okay, that is basically superset of U, not equals to. On this time F of F inverse V is a subset of V, and F inverse F of U, that is a superset of U. Okay, these two are the very important thing in topology. And here U, and my x first belongs to U, so this x belongs to U. So what I can get, I have taken any arbitrary point from F inverse P, that is x. I have taken an arbitrary point x from F inverse P. Okay, and I have got an open neighborhood that containing x, and that is contained in F inverse P. Okay, I am telling another time, I have taken an arbitrary point x from F inverse P, and I have got an open neighborhood U containing x, and that contained in F inverse P. So x is an interior point in F inverse P, and x was arbitrary point. So every point in F inverse P is an interior point. It means, so that's why it implies that F inverse P is open. Clear? So I have my target was to prove that F inverse P is both open and closed, and I have reached to my target. Okay, So, but it is a contradiction, which I have proved that's contradiction, because F inverse P can't be both open and closed in 0, 1. Okay, because in a real line topology, any set without phi and the whole space can't be both open and closed. So the thing which I have proved, it's a basically contradicting thing. Okay, why this contradiction arises? Because I have taken that if possible there exists a path joining 0, 0 and P0. So due to taking this one, my contradiction is arising. So this is not true. There exists no path joining P and 0, 0. Okay, so that's why this deleted comp space is not path connected at all. So it's a very beautiful example, very important thing. Okay, so to watch more videos like this, please subscribe, like, share and comment.